acceleration is like instantaneous velocity. Let's just review here. There's position, which is like how far you're going along here. Your velocity, we often think of this as speed. Okay. But it's velocity. A velocity includes a direction. And then acceleration is, and if you're driving, they're trying to, show you some head positions here of the test dummies. The acceleration is like how fast you're either speeding up or slowing down. So acceleration, think of acceleration as like you're at a traffic light and you hit the gas. Okay. And then velocity is like when you get out onto the road and you're just cruising at a certain speed. And position is like how far you are from your destination. Something like that.
Okay.
So when you accelerate, it can cause, and this is Newton's law, F equals ma. Forces occur as a result of acceleration. When you accelerate, you also cause a force to take place. So let's go to the next image. And this one. So again, it's kind of strange. You get then we get some Kepler's law stuff, but that's not really. You're not really doing any Kepler's law things. We were just using the couple of equations that were given in the book.
Okay.
They emphasize. This is just an aside, I guess, is that the Earth's orbit is more elliptical. It's not a circle. It's
Okay.
and all that means is that there's kind of like this is elongated. It's actually, I mean, it's actually much closer to a circle than you would think, but it's and that's the reason we have the seasons and there's tilts and some other things. So are your exams mostly quantitative, meaning like numerical questions?
What kind of questions do you have in
Yeah.
exam?
Oh, it's like multiple choice questions.
Are they questions like calculate the force, or are they like describe what the force is, and we're like which, what is the force value, or is it, which sentence describes force?
Let me look at one of my quizzes. It's mostly just like determining
The
things.
value of.
Yeah.
Okay. So let's jump to your worksheets, because that will be much more helpful.
Okay.
And do you get a like a reference sheet on the exam, or do you get
Yeah.
formulas provided? Okay. Do you have to write that up or not? Because I can suggest some things to put on there if you you don't. So the eccentricity here of an orbit, this formula is completely correct right here. This is something you might want to have down on there, and it's perfect the way it is. Distance of the foci over the length of the major axis. So they give you these values. They would have to be in the same units. That's why the units cancel out. So there's no units here in this answer. It's just this value here. Okay. And we've done a bunch of calculations here, but if you're going to do this in your calculator, either use parentheses, or like we've been doing 3.08 E6 / 2.45 E8 would be okay to enter this into the calculator. All right, so let's look at the next question. So I remember us working on this question together, and it was an orbital period question. So, another formula again. So the orbital period is established by this relationship here. It's actually starts with p squared equals d cubed.
Mhm.
That's like the formula here. So p is for period. That's p, and d is the average distance. Okay.
Mhm.
One of the things that we did when we worked through this problem before is that the distance, okay, had to be converted into AUs.
Yes.
Okay, and that was a conversion factor that came down here at the end. So like you might just think, oh well, let me just manipulate this number. Well, this number is great, but it's not in the right units. You had to go kilometers or meters to kilometers, kilometers to miles, and then there's 93 million miles in one AU.
Mhm.
And so once you got that value, you can do the calculation. So do you remember doing this?
Yeah.
All right. So let's move on to the next question on here, which was going a backwards question. Hopefully this some remembrance of what we did here. So this question says, calculate the distance between a planet and the sun if the planet has an orbital period of 6.47 Earth years. So you use this relationship again, okay? And they're giving you the value in AU. Okay, they're giving you
Mhm.
that number. So I think we did this slightly differently. Oh, I see what we did here. You converted this number into this one using this equation here, and then you had to convert it back from AUs into kilometers or miles.
Okay.
Okay, so the only equation is this one, but you have to remember that P, I'll write this over. P is in AUs, units of AU.
Okay.
So you have to have that conversion down. Do you remember doing this, or should we go through it again?
Can we go through it again, please?
Yes. Okay. So let's start here with number 2. So calculate the orbital period. Actually, let me snip it in differently. That'll be easier for us to do. All right. Sorry, I'm getting the snip wrong here. Okay. All right, so let's look at number 2 again. So it says calculate the orbital period of a planet that has an average distance from the sun of this number here. So they're giving you D, okay? So you need to convert D, this distance, this needs to be converted into AUs, okay? So it's in meters. So we know down here we have 93,000 miles as 1 AU, but since we don't have miles, we have to convert this into miles. So there's 1,000 meters in 1 kilometer times, well, what's going on here? In 1 kilometer, there's 1.61 kilometers in 1 mile. So see how these cancel out, but we're not quite there yet, because we know that there's 93 million miles in 1 AU. So the point is that this value of D has to be in AUs. Okay, and we have that now. So if you get your calculator out, you'll see that this number ends up being 4.39 AUs. Okay, but that's not the answer. The period squared equals D cubed. Like, this is the equation we want to solve. We want to solve for P.
Okay.
Okay, so you have to undo the square. You undo the square. with the square root. So you take the square root of both sides. So P is equal to the square root of D cubed. You now have your D value. Your D value is 4.39. You cube it and then take the square root. So, and then you get the number there for that. So let's go look at question 3. We'll kind of work through this one again. I think I understand better what you want to do with this session. So let's just work through some problems here again. So this is going the other way. They're giving you P squared equals D cubed. This is the value of P. Okay. So you might say, okay, well, I'll just calculate D. Yes, D is like, if you solve for D, you have to undo the power of 3. So it's 1/3 power. So it's P squared, and then you take the cube root of that, or the 1/3 root. So it's either the cube root of P squared or P to the P squared to the 1/3 power, or however you like that. So we have this number. So this number is here. Okay, so it's D equals the cube root of 6.47 squared. Okay. So now you get this number. And I think you already did this, and we end up getting like 3.47 for that. But that's in AUs because D is in AUs, okay, and P is the period in Earth years. You have to now convert this back into like some usable quantity. So 3.47 AU, and there are in 1 AU 93 million miles. Okay, those cancel. That's miles there. And if we want it in kilometers, we know that in 1 mile is 1.61 kilometers. Okay, so you multiply that out and you get some large number for that.
Okay.
All right, so I see some questions here that have not been solved. Maybe we can do those next. Law of universal gravitation. Oh, you did do them. Okay, 48 kilogram girl. Okay. Let's look at universal law of gravitation. All right, so I'll just snip in a question here. All right, a 6,500 kilogram, I'm sorry, 6.5 kilogram bowling ball is placed 2 meters from another ball. Okay, so here's ball 1, and here's ball 2. This one is 6.5 kilograms, and they're 2 meters apart. And they're telling you the gravitational force between them is this number here, which doesn't mean much to us, but that's FG. So FG in this context is the universal G, which is that 6.67 times 10 to the minus 11, I believe, mass 1 times mass 2 over the distance between them squared. So the universal gravitation, like when you see that on the exam, you want to think this formula right here. And most of the time they're giving you like 3 of the 4, what they're giving you there's only one missing quantity. Like here, we're trying to find the mass of the second ball, which is M2. Okay. And what we suggested doing is solving this for M2, instead of putting the numbers in, just do it without substituting numbers. So just manipulate the equation here. Okay, so you got FG equals G. I'm just rewriting it, M1 times M2 over D squared. So you cross multiply here. Okay, so you get FG times D squared equals G M1 times M2. And again, we're trying to get M2 by itself. So we're going to divide both sides by this G M1, And you end up getting this mass 2 all by itself on the right. So mass 2, I'm just going to flip this around, force of gravity times the distance squared over g times m1. Okay, and then do we have these values? Yes, like they're all given. That was the point of this problem. So the force of gravity is that 1.1 times 10 to the minus 11. D is 2 squared. G is the 6.67 times 10 to the minus 11. And M1 is 6.5. I know that you can do this on your own. I'll just remind you that just be very careful when you put this in the calculator. Maybe an extra set of parentheses down on the bottom, just make it really clear that you're going to do this up top, and then you slash, but you have to multiply these before you divide by that value.
Okay.
You may have already done this one. Yeah. I know there's a number here on the second page, but we'll say 0.1. It looks like it was about 0.101 kilograms. All right, so I'm going to move on to question number 2. And it's another quantitative problem. Sometimes getting the picture is really important. So a 80 kilogram astronaut weighs 1,125 newtons while standing at sea level. So on a planet. So there's a planet not drawn to scale, and there's a person standing on the surface here. They want the radius of the planet. Now it's helpful that you know that you're in this universal gravitation worksheet, because that tells you the equation. It tells you, okay, force of gravity is G m1 m2 over distance squared. This time the problem wants the radius of the planet. Radius and distance are kind of similar. So what I would like you to try to do here is solve for d squared. Solve for this down here on the bottom.
Okay.
See if you can do that on your own. I'll definitely help, but just give yourself a moment, see if you can do that. All right, so let me jump in here. If you cross multiply, you get FG times D squared equals G M1 M2, just like in the previous problem here. Since we want to get D, we're solving for D squared, trying to get D by itself, we want to divide both sides by FG.
Mm-hmm.
So D squared equals G M1 M2 over FG. We're doing really well. So we're going to take the square root of both sides. Okay, so D is equal to G M1 M2 over FG, but the square root of that. And then it's like, okay, do we have these values? And yes, we have most of them. So G is 6.67. Okay, M1, do you want to call M1 the person or the planet? Let's go person, M1. So M1 is 80. M2 is the 2.11 times 10 to the 25th Okay. So we've got those numbers. So we'll start plugging those in. D is equal to the square root 6.67 times 10 to the minus 11 times 80 times the 2.11 times 10 to the 25th all over FG. Now, do we have FG? No, like it's not given up here. Okay. So remember how I told you before there's another equation for F? It's mg. Do you remember that from before?
Oh yeah, yeah.
Okay. So the g here though, really this is F which equals m times the force due to gravity. That's what this g is. It's a notational thing, but they're actually the same. And that's the one you want. That's the one that we're using in this equation down here. So FG, if you divide both sides by m, FG equals F over m. The force is given here as 1,125 newtons. You know that forces come in newtons, and the mass is 80. So we need this number, whatever this number is, and that goes in the denominator of this equation down here. I think we already did that. Yeah, so it's like 14.06. 14.06 down there. And you get a value out.
I have a question. So how do you put in like 6.67 times 10 to the negative 11? Like how would you put that in the calculator?
So we talked about doing this 6.67 e minus 11. Let me show you that. Let me pull up my calculator and see if I can explain that to you. So let me switch screens. There it is. Sorry, these get that faster. Share screen. Okay, so if you're seeing my screen, it's a blank calculator screen. Do you see that? Or not? Do you see this a TI 83?
No.
Okay, we'll try it again. I don't know what you saw then. So do you see the calculator now?
Yeah.
Okay, so if we go 6.67 times 10 to the minus 11, that's one way to do it, but that's not very efficient. So the better way is 6.67 and then this E, so it's second and then E right there, the comma, minus 11. And that's the better way. Say I get the same answer for that.
Okay.
That would be preferred.
Okay.
Okay, so that's the kind of process for those. Let me go back to our workspace and take a look at what you got next. just looking through your through the rest of these pages here, see if anything jumps out to work on. I guess we'll just keep going in the order here that we talked about. I remember you and I working on these, and some of them were more difficult because of the sort of needing to know some of the distances and the masses that weren't given. But I assume those will be given to you on the exam. So let's take a look at this. Okay, 52.25 kilogram girls climbed to the top of Mount Everest, 29,000 feet. Determine the gravitational force that exists between the girl and the Earth. The girl weighs 512.05 newtons at sea level. Okay, so lots of information in this problem. Picture is not super useful, but we could draw one. But she's there's the mountain, and then she's at the top of it. Okay, so this right here, this 512.05 newtons. So if you remember, force equals mass times gravity, but gravity is really this Fg. But at sea level, we know that that's 9.8. So this 512.05 is the force. Her mass, we don't know, but we know that Fg is 9.8. So if you divide 512.05 divided by 9.8, okay, we're going to end up getting pretty close to that 52.25 kilogram value. But that's where it came from. I don't know why the instructor gave you that extra little bit, but they did. And that's why it's in parentheses. Kind of extraneous. This is the mass of the girl. Okay.
Okay.
So we want to determine the gravitational force that exists. So that's the Fg. The Fg is equal to G m1 m2 over distance squared. Now you may be thinking, well, Matthew, didn't we say this is Fg? It is, but it's at the surface. It's not at the top of Mount Everest. Fg changes depending on where you are.
Okay.
Okay. So we're trying to find this. We know G, yay, we got G. M1 is 52.25. That's M1. M2 is the mass of the Earth. That's where you need to know that value, which is 5.976 times 10 to the 24th kilograms.
Okay.
So we got M1, we got M2. Do we have D? Yes. So the distance to the center of the Earth is the radius of the Earth, right? You got the radius of the Earth plus the Mount Everest. So the radius of the Earth is 6.378 times 10 to the 6th. The problem with this is it's in feet. So we got to convert the distance in feet to meters. Okay. So so we can do that down here. It's 29,000 feet times and you had this conversion. I don't know if this will be given 3.258 feet and 1 meter, and that gives you about 8,842 meters. So the distance between them, the distance in this case is the radius of the Earth plus the 842 meters. Right, it's the radius of the Earth plus the height of the mountain here. So we have all the quantities we need. We can find Fg. Fg is 6.67 times 10 to the minus 11. That's the G value. It's the G value up here. Mass 1 is the climber. That's the 52.25. The mass of the Earth, we have to know that value. That's 5.976 times 10 to the 24th. All over the distance between the two objects. So the two objects are the radius of the Earth, which is that 6.378 times 10 to the 6th plus 8,842 meters. That's the Mount Everest squared. So that's the radius of the Earth, and that's the Mount Everest.
Okay.
And believe it or not, you get a pretty decent number there, 511 newtons. All right, let's look at question 2 here. It's kind of the same deal, but it's a slight variation on the same problem. Okay, so let's forget about what this question is actually asking, and let's find the FG, because that's all you know. You know FGG, M1, M2 over distance squared. Okay, so the scenario here is there's an astronaut and there's an Earth. Okay, it's really no different than the mountain. It's just the instead of the mountain, it's an altitude of 237 miles away. So the M1 of the person is 84 kilograms. The mass of the Earth is the same as before. It's the 5.976 times 10 to the 24th kilograms. Okay. G is the universal constant. So we got that. We check, check, check. And do we have the distance between them? Well, the distance between them is the radius of the Earth plus this altitude this time. There's some altitude above the Earth that there. So we need that 237 miles. We need to get that into meters. So 1 mile is 1.61 kilometers, and in 1 kilometer is 1,000 meters. So we get that number. It looks like it's 381,570 meters. So your D this time, your D is the radius of the Earth plus the altitude. The radius of the Earth, that doesn't change. That's a 6.378 times 10 to the 6th plus 381,570 meters. So we've got all the quantities now, all the quantities to be able to do this problem. We've got FG equals 6.67 times 10 to the minus 11 times the 84 kilograms of the astronaut times the mass of the Earth, 5.976 times 10 to the 24th over the distance, which is 6.378 times 10 to the 6th plus the altitude, 381,570, all squared. That is not what this question is asking for, but we need that number. So that number ends up being 733, I guess. Yeah. So 733. Now, so let's go back to what's actually asking, which is how much will an astronaut weigh while in orbit? So your weight is mass times gravity. The mass is unchanged. Your mass is always the same no matter where you are, but the G is really FG. This G right here is really FG. That's the number we just found, which is I actually don't know if we got the right number. I'm going off of your old paper here. Let me check the number real quick, because it does matter here what we get down here. So let me check this. 6.67, 10 to the minus 11 times 84. These are very difficult to enter correctly. So on the exam, maybe enter them twice just to confirm your answer. See if there's any possibility that entered in error. Yeah, so this is 733. That's great. So then that's this number here. So your weight is going to be much higher than at sea level. So it's 84 times 733, whatever that ends up being.
Okay.
All right. We have a couple minutes left. Is there anything like that I can answer, maybe conceptually?
If we could just review friction just a little bit.
Okay. Yeah, let's so this last page, do you have this last page up? The what says name the three types of friction one?
Yes.
I'll step it in here. Just trying to. Okay, so a crate weighing 2,000 newtons sits at rest on a floor. Okay, and it's not moving. The reason it's not moving is there's no force being applied to it. Since there's no force being
Mhm.
applied to it, there's no equal and opposite force of friction, and that's why these are correct here.
Okay.
Okay, but if you start pushing, and that's what's going on in this kind of next scenario. If you start pushing, but you don't push hard enough, it's still not going to move. Okay, so if the person is pushing with 125 newtons, but this thing isn't moving, that means it's pushing back with 125 newtons of static friction.
Okay.
And since it's not moving, there's no kinetic friction until it starts moving.
Okay.
Right, and then the next scenario is it starts moving. So since it's starting to move, or is moving, that means that that there's something there's something that's been broken. Like the static friction is broken. That's why you're able to move it, because there still is friction pushing back. But if you're in motion, that means that your force exceeds the one that that is being provided by friction. So you're doing more than friction's doing back against you, and that's why it's causing it to move.
Okay.
So the static friction, well, these aren't right, but there is no more static friction because it's moving. First of all,
Okay.
the kinetic friction is less than the 225 newtons of applied force. Otherwise, it wouldn't be moving. I don't know. Maybe there's more information here. Maybe I can't tell, but that's kind of my thought here on this.
Okay.
So if it's accelerating, that means F equals ma. That means that the net force, the net F, which is 225, and then whatever friction is, this has to be greater than 0, which is what's causing it to move.
Okay.
All right. Okay, we'll have to end here. Thanks so much for scheduling, and I hope this helps. I'll send you the notes out right away, and I'll see you next time.
Okay. Thank you.
Have a great night. Bye now.
Bye.